Okay, welcome to lecture number 8. So, now today what we are going to do is we are going to introduce periodic crystal potential. Actually, we already did say that because of periodicity in lattice, the crystal potential which electron experiences should also be periodic. As a consequence of that, we did not solve the Schrodinger equation for energy, but we, through Bloch's theorem, we said the solution should be of form the way Bloch's theorem gives, and as a consequence of that, we showed that there is no unique k vector. In fact, two k vectors separated by capital K vector, the reciprocal lattice vector, would yield the same, will give you same properties. So, therefore, using that concept, we were able to show a band, confine the k axis of the Ek diagram to only the first Brillouin zone successfully, and that was one. Second thing we said was that the number of k states in first Brillouin zone would be at least the number of primitive cells that are in the given material. So, those are the two things which I had proved as a consequence of Bloch's theorem, because the potential was periodic. But now what we are going to do is that, having plotted this Ek diagram for free electron, that means the energy is taken hypothetically as the free electron energy, but to show how the x axis, the k axis will be plotted. Having done that, now we need to do improvement on the energy values, and we have to start putting the realistic energy rather than free electron energy values, which are E equal to h square by 2m k squared. Instead of that, we need to put the realistic energy value. In order to do that, therefore, we must introduce the periodic potential into the Schrodinger equation and start solving it. I have told you that solving a realistic equation in a many electron, many body problem is impossible, and we have to reduce it to one electron problem. Even when you reduce it to one electron problem, then you have to consider effective potential, and that effective potential, when you start solving, then it takes huge computer power to solve that kind of thing. Certainly, no analytical solutions are possible. So, what I am going to do is first show the nature of the periodic potential. What I am going to do is simple problem. I am going to show, then I will assume I will show you the nature of the let's go here. I will show you the nature of the periodic potential. I will assume that nature of periodic potential, and I assume that in one dimension only, and using one dimension only, use what is called as Kronig-Penny model. I will show the consequence of this particular potential, one dimensional potential which we apply, periodic potential which we apply, so that physically we will understand what happens. Why, you see, free electron is for metals. Now we are interested in semiconductors. How does this band gap originates from when you apply periodic potential is what I will try to show you from Kronig-Penny model, one dimensional, so that because it gives me a closed form analytical solution. Having shown that, then I will assume that somewhere somebody has done the calculations, realistic calculations, and then I will start showing them for silicon, germanium, gallium arsenide, and different semiconductors in the band diagram. And since you know how to read the band diagram, so then it will be easy, of course. So, today's lecture is about what is the consequence of, and then of course we will show you how the free electron band diagram should be changed when we introduce this potential in there, this periodic potential. So, let us get started with it. So, let us do it like this. Let us look at first an atom. So, suppose I plot the potential. So, let us say I start putting up atom. Here is the atom. Here is I am plotting potential. So, here is position versus, let us say here is a atom sitting right here. How does the potential look like? I am plotting this as a function of position, potential as a function of position. Then this potential looks something like this, that as you approach close to it, the potential behaves something like this, something like this. Now, suppose I add one more atom to it at a spacing of certain periodicity, with certain periodicity. Let me add one more atom right here. If I add one more atom, what happens? If I add one more atom, then I can plot independently for as if that was alone there. In that case, I will plot something similar for that particular atom like this. So, corresponding to this, let us plot this right here. So, similarly, I will plot it for this atom also, a potential for this atom as well, something like this, and therefore, net potential if I plot would look something like this for these two atoms. is going to look something like, as I add up these two, it looks something like this. Similarly, if I plot this for large number of atoms, one dimensional. Now, I am going. So, here is second, here is the third one, here is the fourth one, here is the fifth one, and so on. This is position, and I am plotting the function of position. Then I will plot something like this, and as a sum of all these, then I will start plotting it potential, which looks something like this. And so on. And so on. This potential will start looking something like this. This in our problem. So, this is the realistic periodic potential that we have in our one dimensional crystal. 3-dimensional crystal will be more complicated than that. So, effectively what we are going to do is that we are going to reduce in one dimensional approximate periodic potential. I am going to assume this to be something like this. So, this is the approximation in order to get a analytical solution. I am going to make an approximation, and I am going to make an approximation like this. So, I am going to make it that this periodic potential varies something like this. I am going to use a square potential or rectangular potential is what I am going to use it as. So, periodicity in this, so I am going to use this value as V0. I am going to use this value as V0. This is position. Let us say this is position equal to 0, and let us consider this position to be A. Let us consider this position to be minus B, right here, and right here. So, these are the positions, and this is the periodic potential. That means that periodicity is A plus B. So, this is the, in order to solve this problem which I just described to you, nearly free electron problem which I want to solve in a periodic potential, what I have done is I have taken a one dimensional lattice. In this one dimensional lattice, I have shown how a potential might vary, how the potential might be periodic. This periodic potential, then I am trying to show you, or not show you, but I am going to approximate as a rectangular potential whose value is either V0 or 0 in the range from 0 to A, the value is 0, in the range from minus B to 0, that value is V0, and this is the periodic potential of in periodicity of A plus B. So, this is what repeats itself. So, essentially Kronig-Penny model is about this. I am going to solve this as a Kronig-Penny model. This is the what is called as, in this solution in this form of potential is called Kronig-Penny model, which means that I am going to describe. Let me replot this right here one more time. So, I want to plot it like this. So, I am going to plot something like this. This is the potential, and this is, let us now call this as x direction instead of r direction, because now this is only one dimension, something like this, where this is 0, this is A, and this is minus B, right here is minus B, all right. And so, region, let us call it A. This region A is from x to 0, 0 to A is the region, and region B, let us call it that region between minus B to 0. All right. So, this is the two regions we are going to talk about. In this, the wave function we are going to call it phi of A. In this, we are going to follow wave function as psi of B. These are the two wave function in these two regions which we are going to solve for in this particular problem. Okay. So, what do we have? We have again in this case, So, what we are going to do is, in this case we have a, in this case potential is equal to 0, in this case potential is equal to V 0, that is the potential in region B and region A. So, now what is the problem at hand? The problem at hand is, in this potential we want to solve the Schrodinger equation. So, one dimensional Schrodinger equation. So, what is the Schrodinger equation we are going to solve? Of course, let us write it down now. For region A, what is the equation? The equation will be d square. Now, I can write in some partial derivative, because it is all function of only position one dimension x. So, dx square h square by 2 m a in front of it, which I am taking in a separate form, plus alpha square phi of a of position x, by the way, is equal to 0. And what is alpha here? Alpha is equal to square root of 2 m energy divided by h square. Essentially, in this case V is equal to 0 in this region. In region B, I am going to solve the problem phi b divided by d x square plus, now I am going to write it as beta square phi of b as equal to 0, and this is x equal to a, and this beta now is equal to square root of 2 m energy minus V 0 by h square, where now I have x minus b. So, now I am solving in the region, this region B, I have essentially a potential V 0, whereas potential is equal to 0 in region A. So, I am going to solve these two Schrodinger equation together and apply boundary conditions onto them, and to find solution and how the energy behavior would be. Essentially, that is what we really need to do. All right. So, I am going to do a lot of algebra right now. This algebra I am going to write down here. You are welcome to go through the algebra in details, or you can skip the final result, whatever you like. I am going to write down the algebra, but when it comes to the solution which becomes important, I will point it out. From that point on, you must make sure that you understand completely. Algebra, if you wish, you can skip or you can follow completely. I am going to write down fairly quickly. So, the solution of these equations are of form phi of a should take a form of a of a constant, sine alpha x plus b of a cos alpha x. I am going to write down very quickly on this. So, without too much explanation, sine beta x, if you follow, good, otherwise skip it, but when it becomes important, when we start getting solution, that is where I will expect that you start following again at least more carefully. So, these are the two forms of solution to these two equations. The form of solution is similar for both these equations, because the equation form is same, and therefore, I have written down the solution. Now, we need to apply the boundary conditions. So, these are the boundary conditions which we need to apply. What are the boundary conditions? At point x equal to 0, at x equal to 0, what happens? Phi of a at x equal to 0 should be equal to, wave function should be continuous. That is equation number 1. Equation number 1. Equation number 2 should be that, as you know, the first derivative should also be equal to, that is a requirement on the wave function. That is the nature of the wave function, that it should be continuous at x equal to 0. That is the number 2. Second, as a consequence of periodic potential, remember Bloch's theorem, which says that periodicity is now since a plus b. So, what I am going to write down here is that phi of at the two ends, the wave function should differ by a phase only. And what is that phase? Phi of a at a should be equal to e to power, that is the phase part, j k a plus b, that is the periodicity, in here, and phi of b at minus b. Recall, this is 3, maybe we can change pen. Recall that this is the consequence of phi of r plus r being equal to e to power j k dot r phi to power phi of r. That's the solution which came out of Bloch's theorem, which is exactly what I have written down, where in this case the periodicity is a plus b. In this case, total periodicity is a plus b is the periodicity in here. And likewise, the fourth boundary condition is d of phi a at a dx should be equal to e to power j k a plus b d phi b at minus b, of course, at minus b. These are the periodic boundary conditions, consequence of periodic boundary condition number 3 and 4, and number 1 and 2 are the continuity at x equal to 0. So, these are the 4 boundary conditions, and I have these 4 constants in there, which I need to determine possibly, or I have to solve it as a characteristic value problem. Eigenvalue problem is what I may have to solve this as. So, let us start applying these boundary conditions. If we start applying this boundary condition, then from 1 we will get the 4 equations we will get is, therefore, B A is equal to B B, that is one we will get. Second we will get is, from the second equation we will get A is equal to beta A B. Third equation we are going to get is A sin alpha A plus B cos alpha A is equal to e to power j k A plus B minus A of B, A B is the constant, not A of B, A B sin beta B plus B cos beta B. So, these are the, so our constants are A, B, B, B. So, we are going to apply this. Okay, so, let us just correct this equation. There is a error here, this should be B of A here. So, that is the correction in here. All right. Okay, so, this is the third equation. Fourth equation will be alpha A of A cos of alpha A minus alpha B of A sin alpha A should be equal to e to power j k A plus B beta A B cos beta B plus beta B sin beta B. So, that is the 4 equations in 4 unknowns, but of course, these are 4 homogeneous equations. The 4 homogeneous equations, they always have a trivial solution, that means A, B, and B, A, and AB and BB all are 0 is a trivial solution of this. The thing of it is that, in fact, what we want is that, in fact, if we eliminate, let us do one step first to make it simple little bit. Eliminate AB and B from these equations, these 2 equations, and we get 2 equations which are A of A sin alpha A plus alpha divided by beta e to power j k A plus B. Bear with me all this algebra, this is just for those students who are interested in completeness, otherwise solutions will be very interesting, that I promise. Minus e to power j k A plus B cos beta B equal to 0. Similarly, I can write second equation after eliminating 2 variables, A as equal to alpha cos alpha A minus alpha e to power j k A plus B cos beta B plus B A minus alpha sin alpha A minus beta e to power j k A plus B sine beta b equal to 0. Now, I have instead of 4, I have 2 homogeneous equations in 2 unknowns a and ba. Of course, trivial solution is both of these a and ba is 0, but that is not what we are interested in. We are interested in the trivial solution is, of course, trivial solution is a is equal to b equal to 0 for non trivial solution to trivial solution to exist. The condition is that determinant form by the coefficients should be equal to 0. So, if I so that is the condition. So, in order for non trivial solution to exist, therefore, essentially that is what this is a condition we are interested in, more than solution. We are interested in what the condition for solution is. So, the non trivial solution will exist if these 4 coefficients which you see here form a determinant whose value is 0. So, if I write that out and expand this determinant also, then I will write this as alpha square plus beta square by 2 alpha beta sine alpha a sine beta b plus cos of alpha a cos of beta b equal to cosine of a plus b. This is really the condition for solution. This is essentially what I was looking for. At the end of the day, that in order for solution to exist, this must be true. That is what we wanted to show. I am now going to do a little bit more simplification. Let us call this maybe let us give it a name A1, let us call it A1. This let us call it new and now I am going to solve this problem. Remember, now what happens is the difficulty we have is this, that the solution will take strange forms depending on whether E is greater than V0 or V0 is greater than E. Correspondingly, this beta could be real or imaginary. Accordingly, the solution may start becoming form of solution will start becoming different. So, we are going to consider these as separate cases. All right. So, in order to do so, I am going to separate these out by making certain assumptions, namely, let's not assumptions, sorry, just modifications to how we are going to write it. Now, what is beta in this? So, beta is equal to 2m by h square energy minus V0 square root of this whole thing. This is what this quantity is. So, what we are going to define is, so that we will define beta as equal to j times beta minus or beta plus, so that both these quantities beta minus or beta plus are always real. When this is equal to energy is less than V0 and when energy is greater than V0, then of course beta plus is anyways, then we will call beta as beta plus, in which case anyways it is real. When energy is less than V0, then beta is imaginary. So, therefore, we explicitly written down that as beta minus, so that beta minus is real. Then let us make certain more definitions in there. Alpha naught we will define as a quantity which is equal to 2m h square. In order to give it simplified solution, I am making these reduced quantities. I am going to reduce this called zeta, this zeta energy as being ratio of energy to this potential which is in the crystal. So, that now what is the alpha? Recall that alpha was equal to, we go back to our page 3, alpha was equal to 2m energy by h bar square. So, we use that. So, we can write alpha as equal to, therefore, equal to, remember that was alpha was 2m h square energy whole square. This quantity we can write therefore as alpha naught times square root of zeta. I can write alpha as like this, beta minus as equal to alpha naught by same way 1 minus zeta, and beta plus as equal to alpha naught zeta minus 1. So, I am now going to use these quantities alpha naught, zeta, beta minus and beta plus, and reduce this equation. So, now equation, that condition of my conditions that a solution exists can be rewritten as rewritten as 1 minus 2. This algebra you can try on your own if you want to, but what is important is that this condition of solution is important. This you must understand that this is a condition which we obtained from solution of Schrodinger equation. Now, I am going to a process of doing more algebra and writing this in two explicit form when energy is less than V0 and when energy is greater than the V0. That means when zeta is greater than 1, or when this quantity is greater than 1, or when this quantity is less than 1. I am writing down this solution explicitly for two cases, so that it is easy to follow, so that every number involved is a real number in that case. And sign hyperbolic now, alpha naught b 1 minus zeta plus cos of alpha naught a square root of zeta cos hyperbolic alpha naught b 1 minus zeta, and that should be equal to cosine of k a plus b for when condition when energy is less than V0, that means zeta is less than 1. These are the condition, and this the hyperbolic functions we are using in here. The hyperbolic appears because now this beta will be an imaginary quantity. Similarly, I can write this as 2 zeta 1 minus zeta sine of alpha naught a zeta sine of alpha naught b zeta minus 1 plus cos of alpha naught a zeta. No hyperbolic cosines now, because or hyperbolic cosine or sine and cosine now, because every quantity anyway, since energy now is greater than V0. So, therefore, this zeta is greater than 1. For that condition I am writing now the equation. In that case, simply A1, all the quantities in A1 in any case were real. So, therefore, in equation A1 were real, and therefore, beta was real, and hence we do not have any hyperbolic functions in here. So, cosine of alpha naught b square root of zeta minus 1, and that quantity should be equal to cosine of k a plus b, and this of course for, as I mentioned, energy greater than V0 and zeta therefore greater than 1. That is the condition. So, let us call it as let us call this equation as if you wish B1, and let us call this equation as B2. So, B1 and B2 are these equations now which we are referring to, and this is the condition for solution to exist when zeta is less than 1. That means when energy is less than V0. This is the condition for solution to exist when energy is greater than or energy is greater than V0, and that means zeta is greater than 1 for those conditions. So, now we are going to explore what this solution means. As a consequence of solution, what happens is what we want to explore now. So, let us try to do this. What we are going to do is we are going to plot this left hand side. So, we are going to plot this left hand side for these two functions together. That means, we are going to plot this left as a function of zeta, as a function of this quantity zeta. We are going to plot the value of left hand side when of course zeta is less than 1, we will use this equation B1. When zeta is greater than 1, then in that case we will use equation B2. and then therefore, we will plot this left hand side of these two equations as a function of zeta. So, let us do that. Let us see what this solution means graphically. As an example, take alpha naught A equal to alpha naught B equal to pi. Then plot B1 slash B2 equations B1 LHS, left hand side of B1 and B2 as a function of zeta. Let us see what happens to this. So, let us do this plot. So, what I am going to do is pen here. So, here is my big axis and here is the axis running here. This is zeta, and let us say this is 1, let us say this is 2, let us say this is 3, 4 and here is 5. So, when zeta varies from 0 to this point 1, we use B1 equation, and for all points beyond 1, we use B2 equation. And now, I am plotting left hand side for this condition, for these values taken here. Let us plot this 0, 1, 2, 3, minus 1, minus 2, minus 3. So, let us just plot this function. Let us use a different color pen now. And what I am going to do is, I am put some markers on this also. So, I am going to put this marker here when this left hand side is equal to plus 1 and when this side is equal to minus 1. These are the two markers I am just putting for our sake here. All right. Now, let us start plotting this. So, you just let me see, I want to pass through which points, that is why I want to make sure that I do not. So, this curve goes something like this. When I plot this left hand side, it looks something approximately like this. Process from here. Ever so slightly above and then something like this. So, this curve looks something like this. Now, let us go back and look at these equations. So, this is the plot of left hand side, but what is the left hand side? When does the solution exist? Solution exists only when left hand side is within the bounds of minus 1 and plus 1. Since right hand side is bounded by within is a cosine function and it is real, is bounded between minus 1 and plus 1. So, solution will exist only if these values of left hand side are within plus 1 and minus 1. All values outside beyond plus 1 and minus 1 will not satisfy this equation. Okay. So, now, this right hand side, since it is bound between plus 1 and minus 1, therefore, left solution will exist only when left hand side, which we have just plotted, is also within plus 1 and minus 1, then only the solution can exist. What does that mean? Just let us just quickly write down that right hand side. If you look at the right hand side in that case, so cosine k a plus b is equal to, when k is equal to 0, this is equal to this function is equal to 1, and for k equal to plus minus pi divided by a plus b, this will be equal to -1. This function will be equal to -1 for this condition. So, that is what this will be. So, essentially therefore, I can write now that this value therefore it corresponds to. So, this bound which I am showing you is for k equal to 0, when k is equal to 0, at k equal to 0 this value +1 and of k equal to plus minus pi a divided by b, that periodicity. So, that is where the value of right hand side will become -1. So, essentially whenever this green function, this green curve is the left hand side, when green curve is within these two blue lines, then only the solution exists. So, let us look at this solution. That means the allowed values of this quantity zeta, allowed values of this zeta must lie between here and here. So, this must be the allowed values of corresponding to this and corresponding to this, these must be the allowed values of zeta. This must be the allowed values of zeta. Similarly, corresponding to this and corresponding to this, from here to here should be the allowed values of zeta, otherwise beyond this zeta you can't have values of zeta beyond this, because this function goes beyond either +1 or -1. Similarly, you could have in this range your values of allowed zeta is these, what you are seeing with the blue line, this yellow lines, yellow portion of it, this is where therefore allowed values of zeta are. Which remember is energy divided by V0. So, these are essentially therefore allowed value of energy. Now, you see beautiful result there is that what do you notice in here? Now, we see origin of band gap. That means, now we have allowed, here we have allowed energies, we have allowed energy, but in between are energies not allowed. Not allowed energies in between we have. So, that is now first time we are seeing that metals had no band gap. Free electron theory could possibly describe them. Now, begin to see when you introduce realistic, when you start introducing periodic potential, not realistic yet, there is approximate periodic potential, then you can see the band gap begins to emerge, and that is what is the characteristic of a semiconductor. So, I wanted to show you the where the origin of band gap is, and notice where does this band gap happens. The band gap happens at the edges of the Brillouin zone and k equal to 0. This is the Brillouin zone. Where is the Brillouin zone? Remember, for one dimensional lattice I had shown you the Brillouin zone goes from minus pi by a to plus pi by a, but in that problem a was the periodicity of that one dimensional lattice. Now, in our case the periodicity of one dimensional lattice a plus b now. So, therefore, my Brillouin zone goes from minus pi by a plus b to plus pi by a plus b, and which is this point. So, you can see that at something happens at edges of Brillouin zone, and also where k is equal to 0, that means at the lattice points themselves also something happens, reciprocal lattice points also something happens, and around that point values of non allowed energies begin to appear. So, let us quickly make some observations. What do you see? 1, as V0 increases, V0 increases means what? Notice V0 increases means zeta becomes small and small. V0 increases means zeta becomes small and small, that means we are on the left hand side. In that case, band width is narrow. What does that mean? That means, notice this particular band, it has a small width, allowed values of energies, or zeta allowed values energy has a small range, compared to this which is wider, which is at a smaller, as greater zeta, that means smaller V0, and this is even larger width of the band, allowed energies, that is allowed energies are even bigger, even bigger range, that means band width becomes narrow and narrow as V0 increases, that means we are moving towards zeta smaller zeta, and conversely of course as V0 decreases, therefore or energy increases, then the bandwidth becomes large and large, which you can visualize that if I have a small potential, then until I cross that potential, once I have the kinetic energy, once I have total energy is much greater than the V0, then it will be like that free electron, it will not see the potential. But when I am coming close to that potential, I will see different bandwidths, and as I am going deep into the potential well, then in that case my bandwidths will become narrow and narrow to the extent that they will become discrete, all right, which we will see. Now second, you can see if V0 is equal to 0, if V0 is equal to 0, then what would you notice graphically? You can see that V00 means free electron, that means all values of energy are allowed, continuous band. Now you can see V equal to 0 means zeta is tending toward infinity, and since you can notice that as you go higher and higher in zeta, the bandwidth becomes larger and larger, you can assume, therefore you can see graphically, you can sense graphically that as zeta will tend to infinity, this bandwidth will also become infinite, that means it will become a continuous allowed set of energies. So that is something you should be able to see, that is zeta tends to infinity, in that case bandwidth implies bandwidth is infinite, and that is the case of free electron as we expected, that is the case of free electron as we expected. So then it is possible, if you wish, we can go back to our equation, this A1 equation which we have written down, and you can substitute in there for the case we are dealing with, namely when alpha is beta. So if we take alpha equal to beta and we substitute V0 equal to 0 in there, V0 equal to 0, sorry, V0 equal to 0 means that alpha is equal to beta. So if we substitute it in there, this quantity, then how would this equation look like? Let us do that quickly. Maybe use A1 equation to see this, that is when V0 is equal to 0, then alpha is equal to beta. Remember, alpha beta difference is epsilon energy minus V0, since V0 is 0, therefore alpha should become equal to beta. In that case, I can write this A1 equation as cos of alpha A cos of beta b minus, and remember, let us go back again. So to that equation, alpha is equal to beta, so alpha is equal to beta, so this will cancel out in the what is in the front, and therefore I am writing this cos of alpha a cos of beta b minus sine of alpha a sine of beta b should be equal to cosine of k a plus b is what it should mean. That means if I look at this, then this quantity is cos of what? Alpha a plus b, cos of alpha a plus b, cos of k a plus b. What does that mean? That means alpha is equal to k, and that means energy. And what is alpha is? Definition of alpha is, remember, 2m by h bar square energy. Since alpha is equal to k, therefore I can now write alpha is equal to h square 2m k square, which is what the free electron case was. Free electron case. So that is what the free electron case was. So we can clearly show mathematically also, and graphically you can see also. Similarly, you can do third case also. If V0 tends to infinity, that means you have infinite potential, very large potential. In that case, that means V0 tends to infinity. In order to have a finite strength, simultaneously we will ask this question, that is that if this V0 which I am plotting here, it should have been V0 here, I have been using V0. So this is V0, this quantity is V0 right here. This V0, when this V0 is going to infinity, then simultaneously we are going to demand that this width b also is very thin, almost tending to 0. Then only this can be analyzed, and simultaneously we are going to ask that B goes to 0. If you use these expressions, then now you can see that beta will go to J beta minus, and beta minus will go towards infinity in this case. You can check this out, and if you work through it, you can show that in this case that alpha, in this case alpha, I am not going to go through the whole thing, but alpha you will be able to show will be equal to n pi by a, which then says that energy is equal to h square by 2m pi square by a square n square. Remember, that is a discrete energy levels, like a hydrogen atom. Like in a hydrogen atom, a discrete energy levels, particle in a box problem you will recover from this itself. Try this out yourself, this approximation, consider this as an assignment part, as to how to prove that this energy is equal to this quantity right here, as I have shown here. When V0 goes to infinity and that B goes to 0, in that case try finding, that means of course V0 goes to infinity means zeta goes towards 0. So, use equation A1 to see if you can simplify to this energy. If you can simplify that alpha is equal to this quantity, then you will get your solution, you will get this answer. So, these are few observations which can be made in here as to what the behavior of. So, really striking results we are saying that if you use periodic potential, of course it recovers back when V0 is 0, we recover back near free electron theory. When V0 is 0, V0 is infinity, then we start looking at particle in a box like solution, that means discrete energy levels, and in between for all intermediate values of potential, in that case we start seeing that now as a consequence of periodic potential near k equal to 0, that means reciprocal lattice points and Brillouin zone, we start seeing a discontinuity, disallowed values of energy. So, now what do we do? Now, how do we represent the band diagram? So, approximately therefore, we will represent the same band diagram as follows now. So, let us attempt it again one more time. This is k and this is energy we are plotting, energy we are plotting, and now we are plotting energy as we have derived from Kronig-Penny model. So, now this quantity should be pi divided by a plus b, that is the Brillouin zone, minus pi a plus b rather than just a, because periodicity now is a plus b. So, do not get confused about that, and this is 0, this is k equal to 0 is this point. And now what happens? We know that something happens at edges of Brillouin zone. Remember, at I had shown you that at plus and pi plus minus pi a plus b, right here we are going to go out of this left hand side will go out of -1, and hence those will be disallowed values of energies. Those values will become, I have in this figure, I should also show you that there were some more, there is another band which I have missed here, which is right here. Here is another allowed values of energy which I missed earlier. So, let us use this also. Here is a allowed value of energies in here as well, in between. So, between these two values band gap emerges at these values when it goes beyond -1. So, I am using this idea to show that something, what we do is, so then simply show this curve as follows. So, near the band edge something happens, and we are going to show this by showing it, curve this like this in this form. And what else happens? Correspondingly, remember that red line we had, we are going to correspondingly we are going to show here like this. This curve will remain like this, and we are going to show like this. And since something happens also at these k points when k equal to 0, that means the reciprocal lattice point, and this is reciprocal lattice point. Here is a reciprocal lattice point, 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 where I have marked these points out. So, at these points, since again, so what I am going to do is show these curves in same way, showing that it is almost free electron, like a free electron, except that these special points, this curve changes its shape, and so on. Likewise, I had shown you for green one, I used a green color earlier also. So, I am going to use the same color here also, and we are going to show it like this. We will show this part of curve like this, showing that there is a origin of band gap here. Near these points, there is a band gap opens up, This is how we show as nearly free electron, and these are the band gaps opening up, is what we are trying to show here. Okay, so now if I plot the same these energies becoming now Kronig-Penny model energies. So instead of using free electron energies, we translate them back into the first Brillouin zone, which is what we always wanted to do, or which I showed you for free electron theory also. Then the way we would plot this is, then this red line would now transform into somewhere, red portion of the curve will now transform like this. The red portion will get transformed in this following fashion, and the green portion will then, this particular segment will get transformed in the following form, and this particular segment will get translated in the form where it is like this. And if we continue on this, then similarly we would have, so next one would be then like this, coming out like this, and in the first Brillouin zone I am therefore showing you that there is this, these are the allowed values of energy. So this right here, this is the allowed value of energy, then there is this allowed value of energy, then there is this allowed value of energy. These are allowed values of energies. Then similarly from here on to somewhere here is allowed values of energy, and these are in between the band gaps. This is the band gap. So what I have done hopefully is shown you, right here is also another band gap. What I have shown you is, as a consequence of periodic potential, therefore what I have been able to hopefully convey to you, that the band gap emerges, and in this particular Kronig-Penny model, the band gap is emerging near the Brillouin zone. Remember, that is where the electron wave is strongly reflected. As a consequence of that, this band gap emerges, though we will not get into the physics of how much this quantity will be and what precisely happens, but you get the idea that this semiconductors are, because of this periodic potential into the lattice, into this the periodic potential that is inherent in the crystal. Having done, therefore, having shown you the energies which are somewhat better energies than the free electron energies, and this is a closed form solution I could give you in order to show it to you that what the consequence of periodic potential will be. One dimensional I made the approximation, and the second approximation I made was the nature of the this rectangular periodic potential. Based on that, we could get an analytical solution. On this analytical solution basis, I could show you that the band gap emerges, but from now on we will start using calculated values available in literature, in textbooks. We will use those literature values and put it on the band diagram, those energies in band diagram, and then our nature of band diagram will be more precise, as it should be, which I will start showing you from from one lecture past, not next lecture, but one after that. In next lecture now, what I will do is, given the band diagram has this kind of behavior, what does EK diagram within the first Brillouin zone itself can give you? What information can it give you? Can it tell you about electron velocity? Can it tell you about the effective mass? What is effective mass? What is velocity of electron? What is acceleration? What is momentum of? Can you do dynamics of electron by looking at it? And how does optical properties, how do you interpret optical properties from these band diagrams? Now those are the things we will start discussing in the next lecture, before we start showing the real diagram and start interpreting which is a good optoelectronic materials and which one is not. Okay, so before I end this lecture, let me also just give the finishing touches. Now let's just quickly look at this. So what happened? Let's summarize this. If this is energy, this is the energy axis, then what happened? We got solutions which are like this, discrete energy levels. These are discrete energy levels we had, allowed energy levels, bound electron. Bound electron, when we said V0 goes to infinity. That is what we had in this case. Second case was that free electron, that means all energies were allowed. All energies were allowed, that was the free electron when V0 was going to 0. Intermediate, what we had was like this: allowed energies, a gap, allowed energies, a gap, allowed energies, etc. This is electron in a crystal. That means periodic potential, which I could show differently. This energy versus, imagine like this, that this is, think of this as lattice parameter or interatomic distance. What happens to this energy? Now energy, remember, when atoms are far, let us say silicon atoms or copper atoms are far apart, then what happens? They behave separately. So I have these energy levels, these discrete energy levels, therefore. So I have all these discrete energy levels like this. Let us say this is, we can go to give a name, 3s, 3p, 4s, etc., etc., etc. We can give all these names to them. And suppose there are n such atoms, then I have 2n electrons in each of these, 2n electrons on each of these levels, and they are all sitting on same energy levels because they are not interacting atoms and they are far apart. Now start bringing them close. As you begin to bring them close, what happens to the electrons in this level? Now since they start interacting, so these energy levels will start splitting. If in this case, suppose the smallest energy at this position, when they are so close to each other, at this distance close to each other, this is the smallest energy of these electrons, n electrons or 2n electrons, now start splitting into energy, and I start getting huge range of all these different energy, allowed energy ranges, these different energies which are available to, in which they split. This is the highest and this is lowest. So if I plot only the, what is the lowest and the highest energy available, that means this is at any given A, this is the energy range in which all these energy levels split up. Then if I do so for all these, what do you notice? You notice that somewhere at this case, then I have, these are the allowed energies, these are the allowed energies, these are the allowed energies. At this A value, I am in situation of bound electron. At this situation, we are electrons in a crystal. Namely, these are the allowed energies and there is a gap, and that there is a gap in here in energy. Whereas as I move here, somewhere here, in this region, this is a free electron, all values of energies are allowed. All values of energy become allowed, there is no gap in this case. So you can visualize in physically that where the band gap emerges. Okay, with this let me close the lecture. Thank you.